Okay people, on this one we're going to break trigonometry by deriving d sine theta equals m lambda for a diffraction grating similar to this. You'll remember this diagram probably, or most of it, from the last video. It kind of works here too, so I decided not to get rid of it. I'm going to talk about how sine theta, or the angle that things diffract through, can be looked at in terms of the wavelength, in particular what we can do with white light, and then the application of this in spectroscopy. So you guys have done a little bit of the chem stuff that you've probably seen, the physics stuff that you've seen last year, where you can look at different elements giving off different colours. So the flame colour tests and stuff from middle school somewhere. So to start with, breaking some trig. Alright, so if we pass light through a diffraction grating, we can look at the gap between the slits, or the distance between the slits in a diffraction grating, as d. So we have a number of slits per millimetre. So let's say we're looking at 300,000. So we're looking at 300,000 lines per millimetre. What that would mean is we've got to look at, 300 lines per millimetre, 300 lines per metre. They're generally quoted in lines per mil. What we're looking at is, in this case here, lines per metre. So in this value here, we'll go d is 1 over 300,000. Alright, so it's incredibly small, which is why we can kind of break trig in a little while, sort of in a little bit. The other thing that we're going to do is look at the angle that these things diffract through. So here is the angle. Okay, we should measure this from here, so then you would have it, whatever. But we've got this diffraction angle, so by kind of using the fact that for small angles sine theta equals tan theta, and so on, we can say that this angle up here is also theta. Now, if I want to look at sine theta, I do SOHCAHTOA, so opposite is that guy over the hypotenuse, and in this case the hypotenuse of our triangle is this value here, which is 1 over 300,000. So now I'm looking at this weird, ugly looking thing here. I'm going to rearrange it to get that star on its own. Therefore d sine theta is this star asterisk. So looking at the diffraction pattern, we can see bright, dark, bright, dark, bright, dark, and so on and so on. At this point up here at A, we've got a bright spot. What that means is that we must have an optical path difference of m lots of lambda. Now, here in the middle at B, this would be right in the middle, so the two beams of light would meet there perfectly. We've got m equals 0. So at here, we've got m equals 1. Down here, we've got m equals 1, because the difference is 1. Down at the next spot and up at the next spot, we'd have m equals 2. These are called the order maxima. B in the middle is the 0th order maxima. A and C either side of the first order maxima, above and below on the left and right. So at this point here, for constructive interference, because that's the one we really care about, d sine theta is m lambda because trig broke. Alright, now what this can do for us, if we're using red, or we're using green, or we're using, I should have prepared this earlier, blue, if we're using all of these different colours of the rainbow, even though red's not red, red is pink in this case, if we're using all the different colours of the rainbow, we can see that d sine theta equals m lambda, or sine theta is proportional to the wavelength. So if the wavelength changes, then sine theta is going to change. So as we get closer to 90 degrees, sine theta gets closer to 1. So for this to get bigger, this has to get bigger. So for bigger wavelengths, so more reddish than bluish, remember red's longer, so for the longer wavelengths, the more the light actually ends up diffracting, I believe. Pretty sure that's right. We'll find out in a minute anyway, in the lab, when we do a prac. Alright, the other thing is, what we can do is pass white light through a diffraction grating, and we'll end up splitting it up into the colours, because everything's got a different wavelength, so white light is made up of all of this stuff, plus the Roy Dubuque, is made up of all the different colours, so that means we're going to get all these different diffraction angles. So if we pass torchlight through a diffraction grating or similar, we're going to end up with a whole bunch of different A, B and C values, well B is going to be the same for everything, different A and C values for the first order maxima either side based on the wavelength of the light. So you'll end up having different wavelengths spread different distances from the centre, which means you turn white light into Roy Dubuque, all of the colours of the rainbow. And if you hold a diffraction grating up to your eye and kind of look at the lights in the room, or you look at the blue sky outside, which is kind of whitish light, you'll actually see all of the, kind of looks like a rainbow in there. And that makes it super useful for spectroscopy. So instead of a mix of colours like the yellow that we see when we look at the sodium vapour lamp, we can pass the vapour lamp through a diffraction grating and it'll actually split it up into all of the colours that are in there. And there's some kind of red, there's a little bit of greens, a little bit of purple, most of it's yellow, I get that, but there's still little bits of those other colours. So when we're looking at spectroscopy, we're actually looking through a spectroscope, or we're trying to measure something's spectrum. And using this diffraction grating or spectroscopes in particular, what we can do is look at different heated vapours of different elements and predict incredibly accurately, or find out specifically what they actually are based on not just the colour. You light a fire, it kind of looks orangey. That's because carbon gives off a range of colours centred around orange. If you look at neon lights, they kind of look reddish because they give off a lot of red and not a lot of the other colours. Xenon headlights on slightly older model Falcons nowadays, and they kind of looked a little bit bluish rather than white, because xenon gives off a range of colours, but it's centred, it's averaged out a little bit bluish, as a little bit blue as opposed to the white. Just like that, the sodium vapour lamp gives off, looks yellow, kind of a nice bright orangey yellow colour, and most of it is that yellow, but there's some other bits and pieces in there too. So it can be really useful for looking at stars, seeing what colours they glow, and finding out exactly what sort of gases that they're giving off. And then we can find out how old they are, and some really cool stuff. Right? So hopefully your brains aren't fried from someone else, I didn't do it, someone else breaking trigonometry. If you're really worried about it, we're looking at in some cases 1500 lines per millimetre for diffraction gratings, and we might be, this gap here over a metre might be 30 centimetres if that. So we're looking at spreading something over a metre, not very far, but also we're looking at if we scale this up so that each of these lines were a metre apart, we'd be looking at something like 1500 kilometres distance. So it's here to Melbourne and most of the way back, for this to be fanned out this far. All right, so in terms of scale, this is effectively 0 metres, which is why we can kind of draw two lines here like this and kind of assume that they're actually parallel, which is kind of where these angle things come in. All right, thank you.